Billions of dollars in corporate research, trade secrets, and government intelligence sit unguarded on the desks of thousands of employees around the world. To protect that data, we rely on AES 256 encryption. Mathematically, it is an absolute wall. Cracking this cipher by brute force would require a supercomputer running for billions of years. This mathematical standard forms the backbone of Microsoft's BitLocker, the default enterprise security architecture deployed across the global workforce. Before a machine even boots, a dedicated piece of silicon called the Trusted Platform Module scans the operating system. It checks for compromised code, unauthorized firmware, and software tampering. If the hashes match, the system is cleared. Viewed strictly through the lens of code and logic, the system is mathematically airtight. Yet, the entire system can be bypassed by an individual holding a $5 hobbyist microcontroller. If a machine is left unattended, an attacker needs less than 1 minute of physical access to extract the master encryption key. There is no software bug, no cryptographic code is broken, and no malware is installed. The vulnerability exists entirely in the physical geometry of the printed circuit board. True digital security is impossible if the physical space the data travels through is left exposed. Beneath the keyboard, the motherboard architecture relies on two distinct actors, the main CPU, which acts as the brain, and the discrete TPM chip, serving as the isolated vault. When a computer powers on, the locked hard drive requires the volume master key. To provide it, the TPM vault must physically send that key over to the CPU. Looking at this blueprint, the chips communicate across a physical copper trace called the SPI bus. The flaw is how the data moves. The master key travels in unencrypted cleartext. A basic logic analyzer placed against that trace reads the key out of midair. The vault itself remains impenetrable, but its delivery method is an open, unencrypted public highway. In reality, a discrete TPM chip is incredibly small. Attempting to manually place a metal probe onto its microscopic, surface-mounted pins is difficult for an attacker working quickly. To save manufacturing space, engineers routed the system's UEFI BIOS flash chip onto the exact same shared SPI bus. The attacker ignores the microscopic vault. Because the BIOS chip has large, accessible legs, they simply clip their probe there and eavesdrop on the shared line. This raises a critical question. Why does the system automatically transmit the most sensitive key without first verifying who is sitting at the keyboard? Microsoft designed a defense for this, called a pre-boot pin, which requires user input before the key is ever released. But across the enterprise landscape, corporate IT departments systematically turn this feature off by default. They disable this physical defense layer simply to spare employees the 3-second inconvenience of typing a second password during their morning login. This exploit exists at the intersection of a physical engineering shortcut to save manufacturing space and a corporate policy shortcut to prioritize user convenience. For hardware manufacturers, this vulnerability presented a physical reality that software cannot solve. You cannot patch a copper wire with an update. As long as there is physical distance between components, the data traveling between them is vulnerable to physical interception. Confronted with this physical absolute, the tech industry was forced to reconsider the construction of the personal computer. To achieve true digital security, engineers realized the physical distance between the vault and the brain had to be eliminated. The industry responded by moving toward unified system-on-chip architectures, merging the security enclave and the main processor onto a single piece of silicon. By embedding the security enclave directly inside the main processor die, the physical transit highway is erased. Bus sniffing becomes impossible because the bus no longer exists outside the silicon. But this evolution carries a massive philosophical casualty. Sealing the architecture to lock out attackers also seals it against the owners. It marks the permanent end of upgradable, modular parts. The death of the repairable computer was not solely driven by corporate greed. It was the physical price exacted by the demand for digital security.